Example 1.1. Imagine the charges in 1 gram of hydrogen are separated so that all the electrons and protons are separated by a distance equal to the Earth's diameter. What would be the force of attraction between the electrons and protons and its acceleration? Compare this value to the acceleration due to gravity. A hydrogen atom is composed of a bound state of a proton and electron. Since hydrogen's atomic mass is 1, it turns out 1 gram of hydrogen can be converted from mass into the number of particles, in other words, hydrogen particles, as dictated by Avogadro's number. Avogadro's number. Now that number says that if you have 1 gram of hydrogen, Avogadro claims that you have 6.03, nope, technically 2, times 10 to the 23 hydrogen atoms. But hydrogen is composed of protons and electrons, equal amounts, so that's really 6.02 times 10 to the 23 protons and 6.02 times 10 to the 23 electrons. Converting these to proper charge units So what I mean by charge units here is that we know that the charge of a proton is plus E, whereas the charge of an electron is equal to minus E. So if we want to convert them, we know that the total charge of all the protons has to be 6.02 times 10 to the 23 E, but then converting this, I have 1.602 times 10 to the negative 19 coulombs per electron, and you could see that the electrons cancel, and we're now in proper units. So when I compute this value, I'm going to get a value that's 9.63 times 10 to the 4 coulombs. But because we're dealing with such large numbers, I'm going to say that this is 10 to the 5 coulombs. In other words, we know that the proton charge of all of the protons is about positive 10 to the 5 coulombs, and the charge of the electrons, because there's equal number, is going to be approximately minus 10 to the 5 coulombs. So now we have our charge quantities now. So let's go do this. Now the question says, now only in a classroom scenario can one assume that one can separate these two charges from hydrogen and place them one Earth diameter apart. Of course, this is a kooky belief, but this is a classroom scenario. So if I look at this, I'm going to have my diameter of the Earth. We're going to say that this is the Earth, right? Pale blue dot. And so when I'm looking at this, we're going to take all of those positive charges and we're going to put them right here. And we're going to say that this is Q of the protons. And then we're going to take all of these negative charges and we're going to say that all of the electrons are doing right there. And we can see here that this tells us that the diameter is going to be 2 times the radius of the Earth. So we should define two constants. We can I can look up the radius of the Earth, which is 1.27 times 10 to the 7 meters, which I will approximate to 10 to the 7 meters. And we have our strength constant K, which is equal to 4 pi epsilon. And this guy is 8.99 times 10 to the 9 Newton coulombs meter squared. And I'm going to make that 10 to the 10 Newton per meter squared coulomb squared. So now I could calculate the magnitude of the force. So the magnitude of this attractive force, right? We already know the direction, they're moving towards each other, is then going to be force of the electric force is going to be 4 pi epsilon naught. And then I'm going to take the magnitude of the charge of the protons and the charge of the electrons divided by the distance separation, and that distance separation is 2 the radius of the Earth. squared. So if we start to put in our numbers, it's going to look something like this. So we're going to see that this guy is then going to be 10 to the 10 Newton Coulomb squared. Nope, that's not right. It's meters squared, Coulomb squared times 10 to the 5 coulombs times 10 to the 5 coulombs divided by 2 times 10 to the 7 meters squared. And right away, we could start to look at the cancellations. The charges cancel out. The units of distance cancel out. So then if I compute this value, this will be 0.25 times 10 to the 6 newtons. In other words, I can approximate this again and just say that the electric force is approximately 10 to the 5 newtons. Now that I have that, we can calculate the acceleration. The attractive force causes both charges to accelerate towards each other. However, let's further assume that only the protons move, not the electrons. The acceleration is then, it's going to be the electric force divided by the mass. And we could then approximate this as 10 to the 5 newtons divided by 10 to the negative 3 kilograms, which then gives us 10 to the 8 meters per second squared for our acceleration. This acceleration is incomprehensible to this instructor. It pleads for some perspective. Comparing this to the acceleration due to gravity, we look at the ratio. The ratio shows that A over G is then going to be 10 to the 8 meters per second squared divided by 10 to the 1 meters per second squared, which gives us a value of 10 to the 7. In other words, A over G is this ratio here, and Again, I don't know what this means here, but numerically, this says the protons are accelerated 10 million times higher than gravity. Frankly, I still don't understand. So, frankly, this does not help much. So let's take a different approach. And use kinematics to calculate the time protons cross Earth's diameter. So here's what we know. So if I look at my picture again, I have a positive charge right here. And I'm going to assume that they start from rest. And the only thing we know is that we have this ginormous acceleration. And we know that this thing is going to travel some distance all the way here, which is going to be Earth's diameter here. So it's going to go from here to 2 times Earth's diameter from there to there. So if I set up a kinematics table here, what that means here is that this is one way of organizing it. So I have delta x. So here it's going to be 2 times Earth's diameter. And then I have the acceleration. The acceleration is 10 to the 7 meters per second squared. And then I don't know what the final speed is. I do know the initial speed. And the one thing we are trying to determine is the time. So if I set this up and I use a kinematics table here, this is the variable we do not know. So this immediately tells us that our only equation that we can use is this guy right here. We have no choice but to do this. So solving for time, I find that we have, if I rearrange that equation, we can see here that this term here is 0. So then I'm going to get that the time due to the electric force is then going to be 2 times Earth's diameter, and this is going to be the acceleration due to the electric force. And if I punch in my numbers, this is going to be essentially 4 times 10 to the 7 over 10 to the 7. So that tells me that it's going to take about 2 seconds. 2 seconds to cross the Earth's diameter. Now, if I repeat this, this calculation for acceleration g, we're going to find that the time due to this acceleration turns out to be about 2,000 seconds, which is the same as 30 minutes. It takes 1,000 times longer to cross Earth's diameter. In other words, the cause of the acceleration by the electric force tells us it is very strong indeed.